Okay, let's continue with our discussion of Thevenin and Norton. As a brief recap, these are theories or theorems that were postulated about a century ago. Thevenin theorem was postulated by a French telegraph engineer, and a few decades later, an American telephone engineer by the name of Edward Norton postulated his own theory based off of Thevenin's theorem. Both of these theorems state that you could take a large linear circuit made up of linear components like resistors and multiple sources, and you can represent it as a single voltage source in series with a resistor or a single current source in parallel with a resistor. Okay, and so sweet. Okay, so we had a large linear circuit comprising of resistors, and you had voltage sources and current sources in there. Thevenin's theorem states you could represent it as a single voltage source. Name given to that single voltage source is Thevenin voltage, VTH, sometimes also referred to as VT, and series with a resistor, RTH. RTH is Thevenin resistance, sometimes also known as RT. And then based off of the Thevenin theorem, Norton proposed his own theorem, said that you could also represent that circuit as a single current source in parallel with a resistor, parallel with that same Thevenin resistance. Okay, the current is known as IN, resistance is still the same, RTH. So you have two equivalent circuits for a large circuit. Okay, you have a large unknown circuit, and you can represent it as a Thevenin equivalent network, or you can represent it as a Norton equivalent network. Taking that one step further, since both of them are equal to the same circuit, we can say both of those circuits are also equivalent to each other. Right? A equals X and A also equals Y. Then we can say X is equal to Y. From here, we can also perform a technique known as source transformation. It is something we'll look at the end of this chapter, meaning you could take a voltage source and transform it into a current source and vice versa. The equation that relates the three quantities is, of course, Ohm's law, where VTH is the product of the Norton current and RTH. V equals IR. And then we'll look at how we will determine these quantities. Okay, so your job as an engineer is to determine the three quantities that are listed on here, which is the Thevenin voltage, the Norton current, and the Thevenin resistance. All right. Now, keep in mind, this is not a new analysis technique. Okay, all you're doing is you're applying the techniques you learned to a larger concept. So you're not learning a new analysis technique. That's the absolutely first thing you should always keep in mind. Okay, what you're going to do is you're going to find the three quantities by applying the techniques that we've already learned. You have to find the Thevenin voltage, the Norton current, Thevenin resistance. All three of them are to be determined independently of each other. Okay, so you have to perform three separate analyses to find those three quantities. Thevenin resistance is by far the easiest. Okay, Thevenin resistance is simply finding Req. Again, it's not a new analysis technique. At the beginning of this chapter, we went over the techniques to determine the total equivalent resistance, Req. And that is all you're doing. You take a large linear network that comprises of resistors and sources. You remove the sources from that network, and you find Req between the measurement terminals. Now, the measurement terminals, or as I would like to say sometimes, is the terminals of interest, may be either given to you in the problem, or it would be stated as part of a component. So if it states that you have this network or you have this circuit, find the Thevenin network or the Thevenin circuit as seen by resistor R6, or as seen by the voltage source V7, or as seen by the current source. Doesn't matter what component it is. Basically, the question is saying that you have to find the Thevenin resistance as seen by this particular component. Then you remove that component from your analysis. Remember the example that I began with, right? I said we wish to find the value for R6. Then we analyze the entire circuit by removing R6, and we find all the quantities of interest between the open terminals where R6 was connected, right? And so that's the terminals of analysis. So again, if the question states, find the Thevenin or Norton equivalent circuits as seen by a particular component, then you remove that component from your analysis. That is the absolute first step you should do. Okay, you remove that component from your analysis. When you remove that component, now the terminals are open. Okay, so you remove a component, and you analyze between those terminals. Okay, you analyze between those terminals. As you will see in the example, there are multiple ways of stating this exact same phrase. As seen by is one of the most common. Another one is if you take a circuit and you say this circuit is going to be connected to another following on circuit. So the following circuit then becomes your load resistance that is connected to the first circuit. It'll make more sense when we get to the example. But in all cases, it simply means that that particular component or that particular circuit is not part of your analysis. Okay. Then you wish to find VTH, RTH, and IN. You need to perform 3 separate analyses to find each one of these 3 quantities. Okay, so you have to redraw the original circuit 3 times. You redraw the original circuit 3 times with that component removed, and you analyze each circuit independently. Again, let's say you have the original circuit. CKT is my acronym for circuit. So let's say you have this original circuit. You analyze it 3 separate times. Once for VTH, once for RTH, and one more time for IN. All 3 circuits are independent of each other. Okay, all 3 circuits are independent of each other. They have no bearing whatsoever on the other 2. Meaning if you find the value of RTH in one step, that is a completely different circuit. You do not use those results to find anything else. Okay, do not use those results to find anything else. And I cannot emphasize this point enough. I do not want students using Ohm's law to find any one of these quantities. VTH is equal to IN times RTH, V equals IR. That means if you have 2 of those quantities, you can find the third by using Ohm's law, right? But there are often cases where you cannot find RTH directly because of dependent sources, or maybe because the circuit is connected in such a way that you cannot reduce it manually. Okay? In those cases, you have to find IN first, or IN or VTH. You find IN or VTH, and then you find RTH using Ohm's law. That is different. Okay. As engineering students, you need to have the skill or the ability to find all three quantities independently. So how do we do that? Well, for voltage, you redraw the circuit with your terminals open, and you simply analyze the circuit and you determine the voltage at those open terminals. So let's say we had that circuit, right? That large circuit. Whatever that circuit might be, once you have your open terminals, you find the open circuit voltage at the output terminals, and that open circuit voltage will be your Thevenin voltage, VTH. Yes. Just random examples. This one. Oh yeah, there'll be like 3 examples that we're going to do. We're going to take our time. So again, we take the circuit. If it states analyze between the open terminals, you begin your analysis as it is. If it states find the equivalent parameters as seen by a particular component, then you remove that component from your analysis. That leaves behind open terminals. If you wish to find Thevenin voltage, you simply analyze the circuit by using any method you want, mesh current, node voltage, superposition, doesn't really matter which method you take. You find the voltage at those open terminals. Again, this is not something new. This is you have done this. You have done the homework on node voltage, you've done the homework on mesh current, now you have done the homework on superposition also. So you simply analyze by any method you wish, and you find the open circuit voltage at the output terminals. That is your Thevenin voltage. For Norton current, I'm just drawing in the dashed line, just indicate there's like multiple components in the circuit. We don't really care. Right now, I'm just using it to illustrate a point. If you wish to find Norton current, current needs a pathway to flow through. It cannot flow through the open terminals, so we place a short circuit wire. The polarity of that current, at the beginning of our analysis, we take it as going down. The polarity of the voltage is, of course, plus at the top and minus at the bottom. So we assume that the current is flowing down. And that short circuit current is IN, ISC. Any quantities that you determine for your Thevenin voltage have no bearing whatsoever on your circuit analysis for Norton current, because the two circuits are different. In Thevenin, the output terminals are open. They are not shorted together. In Norton current, the output terminals are connected together with a wire. Okay, so you place a wire if you wish to find the Norton current. You place a wire between the output terminals, you analyze it by any method you choose, and you find the current that is flowing through that wire. That is the Norton current IN. All right, any questions so far? Again, the technique, there is no new technique in here. You're simply taking the techniques that you have learned and you're applying it to a concept, to a theorem. And then finally, we have RTH. RTH is by far the easiest. You take your circuit, open terminals. Doesn't matter what it is, and you reduce all independent sources to 0. which is something you learn for superposition, right? If you wish to measure resistance in a circuit, you have to disconnect it from all power sources that are present in the circuit. So voltage sources, current sources, everything is disconnected. And then you place a short or you place a wire where a voltage source was connected and a open circuit where a current source was connected. Again, these are the concepts you learned for superposition. You simply apply those concepts, modify the circuit. Now all you have left in the circuit are resistors. You find Req between your terminals of interest, and that is your Thevenin resistance, RTH. Req between the terminals of interest or terminals of analysis is your RTH. Again, as I stated earlier on the first day of class, and I stated on the previous class also, this is a 30-point problem in the final exam. I'll ask you to find the Thevenin voltage using a particular technique. I will ask you to find the Norton current using a particular technique. And I will also ask you to find the Thevenin resistance. Okay, yes. Yes, but it's spread over 4 pages and it assesses pretty much entire chapters 1 and 2. It's on the final exam page. All right, think over this. Let me know if you have any questions. Any questions? Okay. Let's look at an example. We'll get into it one example only today. All right, let's say this circuit, which has open terminals right now, right? It just says determine the Thevenin equivalent resistance between terminals A and B. Then you don't need to do anything. The terminals are specified. You begin your analysis as it is. Okay, but let's just say there was a resistor or component connected between A and B. And if it asked you, find the Thevenin resistance as seen by the resistor R5, then your first step should be to remove R5 from your analysis so that you have open terminals A and B, and you try to determine Req between A and B. Okay. So to determine Req, we have to remove all energy sources or all power sources from the circuit. In this case, we have 2 voltage sources, actually, sorry, 2 current sources and 3 voltage sources. So go ahead and draw out the diagram. I'll wait for you all to finish, and then I will draw out the answer here. What are voltage sources replaced with? Right, voltage sources with a short circuit, current sources with an open circuit. So go ahead and draw out the diagram while implementing those changes. Count the number of resistors. You have 1, 2, 3, 4 resistors. Draw everything out. Place a wire where the voltage source is connected and remove the current source. You don't need to have anything for the current source. Go ahead and draw it out and see how the circuit changes. In this case, we are only trying to find resistance, right? So polarity does not matter, and you don't really care how the voltage sources and the current sources are connected. Let me know if anyone has any questions. All right, so here you got R1, R3, R2, and then you have R4 at the far end. A and B. Current sources I1 and I2 are removed, meaning you can draw out the wires or you can just leave it empty. Okay, so they leave behind an empty space. I will draw it out actually just to show or indicate where it was connected. Replace voltage source V1 with a wire. V2 is also replaced with a wire. And then let's see. V3 also replaced with a wire. This was where I1 was connected. And this is where I2 was connected. Does everyone have the same? Anyone have anything different? So now, how has the circuit changed? So if you think back to the beginning of chapter 2, if you wish to find REQ for any circuit, then we start at the farthest end. You can use any technique, right? The technique I showed in class, the two horizontal lines, parallel lines, or if you're familiar with your own techniques, you can go ahead and use that. But if you start at the farthest end, we see R1 and R2 are in parallel. So I'm going to write R1 and R2 in parallel, which is then in series with R3, and which is then parallel with R4. As we go on reducing, keep track of all the nodes. You can label the nodes if you want. Okay, as long as the resistors are connected, both terminals of the resistors are connected to the same two nodes, then they are in parallel. Okay, if there's anything in the wire, then they are not in parallel. If they're connected at one terminal with no more than two connections, then they are in series. Okay. And so we start at the farthest end, R1 parallel R2, which would be in series with R3, and then parallel with R4. That would be your total REQ. And that is your Thevenin resistance for this circuit. That's it. As straightforward as that. So again, it's not a new technique. You're simply taking the technique and you're applying it to a concept. Okay. This is one of the most important concepts in electric circuit analysis. So please take your time, review this, and we'll look at example problems in next class. Okay. Let me know if you have any questions. That's it. There's no values. The next two yes.